Hi, and welcome to Software Design Development Implementation Lesson 5, Role of Machine Code in the Execution of a Program. Here are the dot points covered for this lesson. If you want to read them, pause and you can. And again, every lesson you should be taking notes. I've copied this slide from yesterday obviously, but you need to make sure you take notes. Again, this is a very, very dense lesson. A lot of new content you haven't seen before, so you need to pause now, get some note paper or open a Word document or something and make sure you take notes. As you should know, there are a number of types of code. We've got machine code, which is the ones and zeros which the computer reads. We've got assembly language, which is a series of 2 or 3 letter abbreviations that is specific to each processor. Each processor has their own version of assembly language. This will be translated to machine code when it needs to be. And we have the 3rd, 4th, and 5th gen languages, which are written in code resembling English, with English terms and English structure, enabling the programmer to code things a lot easier. And this also allows it to run on a range of processors. There are other differences, much more important differences, but these are the ones that we care about for this topic. Okay, and for this lesson we're focusing on machine code and assembly language. So the format of machine code varies as each processor uses a different variant. Okay, in the HSC you'll be given a key to interpret because you can't learn every variant of machine code out there, and we won't expect you to. So the variant we'll be using for the lesson when you come to class will be something like this, where you see 1, 2, 3, 4, 5, 6, 7, 8, and this represents the number of the bits in a byte. So there's 8 bits in 1 byte, obviously. And this 3 represents something, these 4 represent something, and this 1 also represents something. Okay, so the first 3 bits will be an operation as follows. Okay, so in 3 bits there are 8 possible values, and you have your 8 possible operations here. The next 4, okay, so we can see, remember there was 4. The next 4 represent a specific location in RAM. Okay, we have locations 1 to 16, as we can specify 16 locations with 4 bits. And the last bit signifies which register to use. Okay, 0 indicates register R1 and 1 indicates register R2. For operations do not require a register, this is set to 0. Here's an example of an instruction. Okay, so 0011 1110. If we break that up so that we can read it easier, we can see that 001 is a read operation, which means we're inputting a value. 4 ones would be memory location 15, because that's the value of 15 in binary, and we have 0, which is the register location. Okay, so we have registers and accumulators. So a register is a temporary storage area. It's used to store data needed for the current calculation. And there are also special types of registers called accumulators, which store the current value of the calculation. An example we can see in the Heinemann text, and the code we have is sum equals sum plus value. Okay, when we change that to machine code, we get a whole stack of 1s and 0s, but translated that to English, we get something along the lines of: load the accumulator with the value from memory location 469. Add the value stored in memory location 490 to the accumulator. Load memory location 469 with the contents of the accumulator. Obviously these numbers are made up, but they're just representative of what could be a valid instruction. So here's a series of pictures that demonstrates. The first thing we do is we take the information from memory location 469 and read it into the accumulator. The next operation will take the next piece of data from memory location 490 and read that into the ALU, and it will also take the information from the accumulator into the ALU. The ALU will then add those 2 values together and then put the result in the accumulator, and then that result will go from the accumulator through the ALU to the memory location 469 to be stored. Okay, other important things we have are program counter. A program counter is a register that stores the memory location of the next instruction. Okay, generally it will increase incrementally, but it doesn't have to. It can jump to any location it needs to. For instance, if you have to end an if, that doesn't execute. Okay, Another thing we have is a stack pointer, and a stack pointer is a register that acts much like the program counter, except it's used when a subprogram is called. The stack records the value of the program counter when it needs to jump to another location to perform a subroutine. Okay, and at the conclusion of the subroutine, the value of the stack pointer is copied back to the program counter so it doesn't lose its place. And it's a last in, first out list, meaning that the last value into the list is the first one read out of the list. The Heinemann textbook makes a point of treating this like a stack of plates. The last plate you put on a stack of plates is the first one you take off it. Okay, so here is a slightly graphical representation of this at work. We're running a program. Just so you know, all the line numbers here are arbitrary. I've just made them up, okay, but they are representative of what could happen in a program. So on line 152, we have a subprogram called sub1, and it's called. The program counter is then written into the first address of the stack pointer, which is memory address 700. Moving on, we can see the program counter is reset to 300, which is the first instruction of sub1. As sub1 runs, it decides to also call a subprogram called sub2. Okay, the stack pointer is increased to 701 to indicate we're looking at a new section of the stack, and we write the new the new program counter 306 to 701, and the program counter is reset to 500, the first instruction of sub2. As sub2 runs, it also calls a subprogram sub3, and it calls it on line 552. So the stack pointer is increased to 702. The contents are changed over here to be 552, 702. And the next step, we can see the program counter is reset to 600, which is the first instruction of sub3. Moving on, sub3 runs, it doesn't call a subprogram, and it finishes on line 624. Okay, when it finishes, the program will look at the stack pointer. So the stack pointer used to be 702, and so it says, right, take 552, drop it over here, so make that the new program counter, and then reduce the stack pointer by 1. So as we reduce it, what we're saying to the computer is, we don't need it anymore, you can use it again. So it doesn't actually overwrite the contents, but because the stack pointer is reduced, it's saying that this can be overwritten should it need to. So if this sub2 would call another subprogram, it will get rewritten. Luckily for us, sub2 doesn't call another subprogram, and it finishes on line 560. And so on line 560, the program counter is changed to 306, which was the contents of stack pointer 701, and the stack pointer is reduced by 1 to become 700. Again, signifying to the computer that we can reuse this value should we need to. Sub1 also finishes on line 342, which means the original program counter when we started this subprogram stuff, 152, becomes the new program counter, and we can begin where we left off when we called the first subprogram. Okay, I also talked about the linker in the last lesson. Basically what the linker does, during translation, the linker will enable a program to call a variety of subprograms. Okay, and the subprograms could be ones the program has written. They could be standard code in the programming language, such as that used to to calculate the square root of a number, or it could be code to perform an operation in the operating system, such as opening a file. We also have this thing called a DLL, or a dynamic link library, and what it is, it's a standard library, but it's a special one because what it allows you to do is it allows you to update the library without recompiling code. So when the code is run, after it's compiled, it will look for these subprograms in the link library and then take the instructions from the link library and load them into RAM. If the link library changes after the compilation of a program, it allows it will just take the updated program. So you can update a compiled program without having to recompile it. You can just change it by using these DLLs. Similar to what you guys understand happens when a game is patched, for instance. So how do we join all this knowledge together? To do that, we have to look back at the fetch execute cycle, and this is something you learnt back in year 11. So the fetch execute cycle The instruction is fetched from RAM, okay, and is sent to the control unit. The instruction then is decoded. The control unit works out what needs to happen and sends this through to the ALU. And the ALU is the part of the processor that actually does the processing and executes the instruction. And the result of that instruction is then stored in RAM. Extrapolating this to what we know about memory instructions, here is an example of our new understanding. So the fetch part of the fetch execute cycle means get the instruction location, get the instruction, and increase the program counter. Okay, I'm not going to run through all of the extra steps that you now understand in the fetch execute cycle, but you can work out what they are through your knowledge of memory locations and through what the fetch execute cycle does.